We're going to use this cool vintage Dodd and Struthers lightning rod, which I believe comes from the early 20th century. It was in the storeroom at Manchester High School. We're going to hold it up to our Van de Graaff generator, and we're going to use this to demonstrate how it's not able to hold large amounts of charge before discharge happens. Alright, so we watch as I bring the sphere on the end of the discharge wand. You can see how close I can get before we get a lightning bolt. We can see a similar result as I bring my hand close. That's how close I can get my hand. But watch how close I can get the lightning rod. I'm hearing it discharging. There's little tiny bit of light that I can see that you probably can't. But I can get this super close without a large discharge. Again, it's because the lightning rod tip can't hold large amounts of charge. If you go ask people on the street, what's a lightning rod do? Most of them are going to say it attracts lightning. As if it's like some sort of sacrificial lamb, like, hey lightning, hit this, and not this other stuff. It's actually not the goal at all. The goal of a lightning rod is to bleed charge, so that large charges don't build up, making lightning less likely. If the lightning rod is working right, lightning hopefully doesn't happen at all. It accomplishes this by coming to a sharp point at the top. That geometry allows less charge to get held there before lightning discharges. It's actually the opposite effect of the Van de Graaff generator. We want to get pretty big sparks with this. That's what makes it useful and cool to do stuff with. So it's got a ball on the edge, the opposite of a sharp point. And it allows a lot of charge to build up before we have a spark. So the goal here is to build up sparks. The goal here is to make them go down. So why would that be important? Well, if you can leak charge constantly, and you don't have large charge buildup, that means you're not going to get electrical damage. Damage is caused by transfer of energy, when the lightning does work on something. The energy of electricity, the potential energy of electricity, it depends on the energy per charge transferred, called the potential. We talked about that in another lesson. But also the amount of charge that transfers. So even if you have huge differences in energy per charge, if you only have a small number of charges transferring, you don't get much damage. So that's the goal. A lightning rod, because it's constantly getting rid of charge, never builds it up. So damage doesn't happen. A ball, on the other hand, builds up charge more and more and more, and you could have damage. So how does this work? The bottom line is air is an insulator, and like any other insulator, at some point an electric field can become so strong it rips the air molecules apart. Air, this happens at about 3 million volts per meter. So the goal is to get to 3 million volts per meter with only a small amount of charges. Then you're going to get a discharge, and it won't be violent. If you get to 3 million volts per meter and a lot of charge is built up, then you get a big energy change. So how does a lightning rod accomplish this? Let's draw some electric field pictures, and I think we'll see. I've got three things here: a large sphere, a small sphere, and a lightning rod. And I'm going to put some charges on them. Symbolize the first charge, I'll put 4 plus signs. In reality, of course, this is billions and billions of electrons lost to get these positive charges, but 4 is easier to draw. So we got our 4 charges, and now we're going to draw the electric field lines. Now, electric field lines, we've talked about that in another lesson. They are the direction of force on a positive test charge. So this positive would be repelled by this guy, and that tells you the electric field lines will be out of all of these objects. So I'm going to symbolize the electric field by drawing 8 lines coming out of each object. Now obviously you could draw electric field lines forever. There'd be an infinite number you could draw because there's an infinite number of directions you can be pushed away from a circle. But essentially, for each amount of charge you have, you decide how many you're going to draw. And you're just consistent. All of these are getting 8 lines because I decided 4 charges get 8 lines, and all of them have 4 charges. If we had 8 charges, they'd have twice as many. 16, they'd have 4 times as many. So these pictures show us how strong the electric field is at any given point. We basically said, here, because these lines are so far apart, they show a fairly small field. But here, they're even farther apart, so the field has shrunk more. So the closer together the lines, the stronger the field. We'll get rid of that. I think you can see now that for the same 4 charges, my smaller ball has lines closer together. So instead of a smaller field, it's got a medium-sized field. My tip, because the lines are so close together, because the charge is so concentrated in one place and not spread out like here, I have an enormous electric field. And I did it with a small charge. If we get past the dielectric breakdown point, that means we get a lightning bolt. But it's only the smaller charge Q. We wouldn't even notice this. The charges would just move away. What happens to these guys? Well, in this case, charge continues to build. So let's add in some more charges. I'll use a different color. We'll put 4 more in. Now we've got twice as much charge as we had there, so we've got to put in 8 more field lines. Well, that I think shows us that the electric field has gotten stronger because now there's less distance between the field lines. So instead of a small electric field here, we're going to have a bigger one. We'll say it's medium here. And here, it's getting to large. So maybe this is now at the point where we have dielectric breakdown. But now we're transferring twice as much charge to Q. So maybe we're going to do some more damage. We got a lightning bolt. We still haven't had lightning here yet. Let's throw a bunch more on there. Let's throw twice as much as what we currently got, so there's 16 of them. So that means 16 more lines. And now finally, we've gotten to the point where our electric field is strong enough. And you get a lightning bolt. But now it's got 4 times as much charge. And maybe that's enough to do some damage. So the goal of a lightning rod is to not let charge build up and cause problems. Get rid of charge when there's only a little bit, less destructive lightning. I want to look at a part of the Van de Graaff that often gets overlooked. and that is the discharge wand. And it's very important how it's set up. If you look, there's a wire coming off of it, which is actually clipped to the base of the generator, which is a conductor. It's made of metal. And that metal case, and therefore the wand, are actually hooked up to the earth itself through the power cord. If we go over and look at the plug-in, we can see that there's 3 pins. And the 2 flat pins are the ones that actually provide the electricity. The round pin is called the grounding pin, and it goes out through the wiring of the school, and it goes to a pipe that's sunk into the earth somewhere. The point of this is that the earth has lots and lots of electrons. And that means electrons can come up this wire, and they can go to the base of the Van de Graaff and the wand. Or if there's too many on there, they can leave. And that's going to help us understand how the wand can actually cause lightning bolts near the Van de Graaff. But there's one thing that may be confusing. It's not clear how the lightning rod or the discharge wand was getting charged. Obviously the Van de Graaff was, but what was happening with the rod and the wand? Let's start with the wand. Because it's wired to the earth, as I just showed you through the plug-in, it can have the earth's electrons if it needs them. And the earth's electrons are noticing that they have a path up that wire towards the Van de Graaff. And into this wand. And they like that because that gets them closer to a positive charge. So in other words, the running Van de Graaff induces a negative charge in the wand. And that induced negative charge can be fairly large in the spherical shaped wand. It can't be so large in the pointy lightning rod. I'm not hooked up to the earth, but I still do have a lot of electrons. And they get drawn to the tip of that lightning rod through me. And we get a lightning discharge, or a leaking of charge, much sooner because the lightning rod had a pointed tip. Here enough charge could build up that eventually we had a large lightning bolt.